SwayamPrabha. Digital India. Educated India.
Hello everyone. So, we are discussing the different factors which influence the impact performance. So, the factors are broadly divided into two parts. One is fiber, yarn or fabric related characteristics, and next is the projectile related parameters like shape of the projectile, weight and all these parameters. So, in our last session we have discussed the different fibers used in protective textiles, that ballistic protective textiles. These fibers are para-aramid, PBO, ultra high molecular weight polyethylene, inorganic fibers that we have discussed. And among the fiber properties, the different properties are important, that also we have discussed, like it should be high modulus, tensile strength should be very high, density should be low as possible. So, elongation should be lower, it should have good resilience in tensile deformation, it should have low moisture retention capability, high thermal stability should be there, high limiting oxygen and stability in extreme conditions. This we have discussed, and also we have discussed in detail the effect of twist, and we found that there is a, if the twist angle is more than 5 degree, then that performance deterioration will be at faster rate. Next is the sweep pattern. Sweep pattern actually affect the ballistic characteristics in a greater extent. So, we have two different types of weaving pattern. So, one is 2D structure and another is 3D structure. So, in among the 2D structure, so plain, basket, twill, satin, they are very prominent, and main requirement is that we should try to keep the fabric structure as a square fabric structure. So, what is square fabric structure? Basically, it is a, you can say it is a balanced fabric where the warp side and weft side effectively their characteristics are almost same, exactly. We try to keep the characteristics, maybe thread density, thread linear density, even crimp, all these parameters we try to keep same. So, square plain fabric we can use, even basket weave is used, these are very common. Apart from this, twill and satin are sometimes used, but twill and satin, the main problem is that due to their lower interlacement, the thread, this warp and weft slippage, that thread distortions are easy. So, that is why the plain and baskets are most commonly used here, and angle interlock in case of 3D structure, angle interlock, warp interlock and orthogonal structures are very commonly used. So, if we use the plain fabric, there will be definitely the advantage is that thread distortion will be less, but at the same time the plain problem is that the impact concentration will be very high because of the higher friction, higher contact area. So, that we have to see in that direction we have to think. Next is the very important characteristics is the cover factor. So, cover factor should have certain range, it should not be 100% jamming. So, cover factor range should be around 0.6 to 0.95, that is the recommended range we have to keep. So, problem would be there if the cover factor is more than 0.95. So, in that case there will be jamming condition and yarn damage may take place during the weaving. If we try to have higher cover factor to enhance that protection performance, in that case there may be damage in the yarn. So, that we have to control. So, maximum cover factor is recommended is 0.95, and on the other hand if it is a loose structure, so cover factor is loose, then the projectile can penetrate very easily. So, easy penetration of the projectile if it is the loose structure. So, the cover factor should be optimum. Next one is the crimp. So, ideally there should not be any crimp if we want to actually utilize the yarn characteristics or fiber characteristics in a greater extent. So, higher crimp, the projectile resistance will be low. So, as the crimp increases, the projectile resistance will be lower. So, let us try to understand this aspect. Suppose there is a crimp, this may be warp or webbed, A. Another with a higher crimp, B, and third one with the almost there is no crimp, C. 3 types of fabrics are there. Now, if we have B with the highest crimp, in that case, now let me draw. So, this is fabric B with highest crimp. Now, here what will happen in case of any impact, projectile impact, there will be straightening of the crimp, okay, and due to this straightening there will be more deflection. Suppose it is a, so the projectile will penetrate. So, before the yarn or fiber start resisting, there will be straightening or removal of the crimps. So, there will be removal of this crimp and the projectile will penetrate. So, resistance to the projectile will reduce. So, that is why with the increase in crimp, the projectile resistance will reduce, because the fibers or yarns, before the yarns or fibers are under stress, the share the stress, there is a large deformation of the yarn itself due to removal of crimp, and then the wave, that the energy dissipation will be reduced. So, that performance, that impact resistance performance will reduce. On the other hand, with the increase in crimp, transverse way deflection increases, okay, and the blunt trauma increases. That is what I have here. If it is increasing, then there will be a back face, higher back face signature, because it is actually deflection will be very high. So, transverse way deflection on of the fabric will be more. So, crimp has to be optimized. Next is the friction. Friction, which plays a great role in ballistic protection. Friction, that means friction between yarn, between fiber. So, even friction between the projectile material and the fiber. So, everything they are very, very important. So, the best optimum friction, it has been observed, it should be around 0.2 frictional coefficient. Okay. So, as the friction of the yarn increases, so more yarn takes part in the failure mechanism, and that is why energy absorption increases. Now, let me explain. This is the fabric where the yarn to yarn friction is low. Another fabric where yarn to yarn friction, here yarn frictional coefficient is high. Suppose here frictional coefficient is say typically 0.1 mu, here mu is say 0.3, more than 0.2, here less than 0.2. Now, what will happen here when a projectile strikes? Suppose there is a projectile, there is this is the projectile striking from one side. So, it is striking there, and here is a projectile, it is striking. Now, what will happen here with a lower friction? So, if it is acting on that, on the particular yarn, due to the sliding, easy sliding as a lower friction, it will not be able to take the more and more yarns, because the yarn which is under stress, it will simply slide past the other yarn, and the main load will be concentrated, main load will be on the less number of yarn. But in case of higher friction, that means here there will be, we can assume that there is a high friction and there is a locking, more prominent locking will be there. So, this total structure will act as a unit structure, but here there will be movement, thread to thread movement will be there. So, it will this with a low friction the total entire structure will not as a unit. Here this will act as a unit. So, when the load is coming into a particular thread, it will take the other threads. So, for that is more friction, so that means more and more yarn will take part in absorbing the energy. So, in that case the total the ballistic protection will be increased. Another case, suppose there is a lower friction. In that case what will happen, this is the fabric structure and there is a ballistic projectile hit this way, projectile is hitting. What will happen, the yarn where the projectile is coming directly striking, that yarn will be pulled out on the other side. Okay. And due to this pull out and at the low friction, that pull out energy will be lower. So, that protection will be lower, but on the other hand in case of high friction, that yarn pull out force will be high and it will absorb more energy. So, that is why for higher friction both the higher pull out energy will be there and also number of yarns coming into absorbing the energy will be more. So, those two advantages are there, but there is a limit. If we have very high friction, at very high, because we need certain movement of the yarn, otherwise at very high friction the localized stress development will be there, that localized stress concentration will be there, and at that case that slight movement is required because that the energy dissipation will be there. So, localized stress concentration will be there and easily the yarn breakages, that will also will affect. So, energy absorption will reduce. This is actually similar to like tearing action. If the friction is very high, yarn to yarn friction is very high, there would not be any yarn sliding and tearing strength will reduce. So, friction plays a great role. Typically, we have to increase the friction for all like energy absorption and more pull out force. So, we need effectively higher pull out force. And next parameter is the number of layer. So, here this is the friction, you can see with a point 2 friction we get the energy absorption keeping all other parameters constant. So, here at 0.2 friction level what we found that the energy absorption is very high. And as we increase the friction level from 0 mu 0 where there is no friction, ideal case. So, the energy absorption gradually increases, that we have observed, but at very high friction where friction is say 1, very high friction, it will the energy absorption drops. The reasons we have already discussed. So, obviously, the number of layers, as we go on increasing the number of layer, the ballistic limit, the speed will increase, ballistic limit will increase, that we have already discussed earlier, because number of layers if we increase, it will absorb more and more energy, it needs more and more energy. So, we have to have higher velocity for penetration. So, ballistic limit the speed will be increasing. So, as we increase the number of layers, now here we can see we have used plain and satin. So, satin gives the requires higher speed here because of the float, and the cover factors are have kept constant. So, because of the float, the yarn little bit movement will be there and it will absorb, it will help in absorbing the energy. So, but the problem here is that say up to 35 layer. So, if we use higher number of layer, the fabric's flexibility will be compromised and the weight will increase. So, we have to compromise the between the protection and the weight. So, but the overall with the increase in number of layer, the protection level or ballistic limit will increase. So, fabric number of ply, trauma dimension is. So, if we increase the number of ply, so the trauma dimension, so trauma that is depth of trauma, like back face signature, if we can say, this gradually it is generally it is reducing, because number of ply it becomes little bit stiffer, and the if we use and the next layer will keep on absorbing the whatever this energy it will start absorbing. So, that at the last layer the deflection will be lower. So, if we go on increasing from 20 to 30 or 35 layer, it will gradually reduce, that trauma dimension will reduce. Now, the different layers, so number of different layers we can stitch together, we have to stitch together, but stitching can be done in various ways, and to make it a single unit. So, there are different types of stitches are there. Here the stitch is at the from the side, this is type B and type C, 3 different types of stitches were studied, and what it has observed, there is no such significant changes are there in, although the type C shows little bit lower trauma dimension, that means the back face signature is reduced, that is due to the proper grip, as the number of stitches are more, that is the that free layers are less. So, in that case the proper this transmission of load from one layer to another layer, because this structure is intact, much more intact than other structures. So, that is why there is a slight reduce in trauma dimension. And here you can see there is a energy absorbed by different fabrics. Okay. Now, F1, F2 are woven fabric and F3 is knitted fabric. So, if you compare the woven fabric with knitted fabric from same fiber para aramid, So, what we have observed here, so projectile energy loss for woven fabric will be, see this is the woven fabric, here is much higher than the knitted fabric. So, that energy absorption by the fabric will be much higher in case of woven fabric, because the knitted fabric, the main problem is that it is stretchable. So, it gets extended and the projectile energy absorption will be low. On the other hand, if we compare the woven fabric of nylon and Kevlar, so Kevlar for certain layer, Kevlar's performance is much higher than nylon. So, you can see here, so number of layer, even Kevlar with 2 layers is equivalent to nylon with 4 layers. So, that Kevlar's performance is definitely higher depending on the fiber characteristics. Kevlar is much stronger than nylon. Now, we will try to understand the different fiber properties, okay, on impact behavior. Here the speed of the longitudinal strain wave is one important characteristics, which will actually control the speed of the longitudinal wave, because that whenever there is an impact on a fabric, there will be a longitudinal wave generated, which will help in dissipating the energy. So, this speed depends on the fiber characteristics. You can see here, this is the fabric which is made of fiber, and when the projectile hits at speed say v, at the speed, the fiber will get stressed. So, although projectile is hitting on the right angle downward direction as per this picture, the fiber will be stressed in the horizontal direction, and due to this there will be longitudinal wave on the fiber. So, this is the at the longitudinal wave front. So, fiber will get stressed and there will be stretching of fiber, and this wave, this is the wave front, and this wave will go on in this side direction. Now, the speed, if we see, if we want to calculate the speed of the longitudinal strain. So, that strain here it is, these fibers are straining, this initial, suppose diameter of the fiber is this, after straining the fibers become thinner. This strain, initially the strain will start at this point, but it will gradually fibers get strained, and the speed can be calculated based on the modulus of fiber and the density. That is very important. When we suppose this is a material, when we there is impact, projectile impact in this direction, it will get pushed. So, the strain will start from this point, strain will start from this point, and gradually strain will move in this direction, and this is the wave front. So, the wave will go in this direction, okay. This is the front and it will go in this direction. Similarly, here also this is in there. So, the wave front will move against the direction of the load. and this in the at slow motion, okay, quasi static motion. So, this does not happen there in a normal stress condition, normal tensile strength of any fiber, there is no wave front generated. Normal loading, suppose this is loading in a UTM, this is a filament it is loading, the strain will be uniformly distributed as depending on the entire strain. But in case of impact, here, so this is the, and here is the impact, the strain will start at that point, impact point, and gradually it will move in this direction. So, let me explain the wave front clearly. Suppose this is a fiber of this size, this is the original size of fiber. Okay. Now, when there is a strike here, projectile strike here. So, next this is one, next picture will be this is the way. That means, from this point there is a stretching. Okay. So, this will move in this fashion, and this will become wave front, and it is stressed in this direction. Third picture. So, this will be the type of so, this is becoming wave front. So, wave will be, that is strain wave will move in this fashion on the other direction. The stressing is there, this is the strain wave direction, but stress will be towards the impact point. So, I will draw in the other color. So, this is the strain wave direction. Okay. So, this speed of this wave, this is the speed is, it depends on the fiber characteristics. We can control this strain wave speed. So, this is the longitudinal wave here, the c is the speed of the longitudinal wave, E is the initial modulus of the fiber, and rho is the density. Now, if we want to increase the this wave, strain wave quickly enough, because otherwise the load sharing, that distribution of the this energy will not be faster. This wave front movement should be faster. So, how can we do? Either we can increase the initial modulus. If we increase the initial modulus, then the C can be increased, or we can use a fiber with a lower density. So, if you reduce the density, then also C can be increased. Our idea is to increase the speed of the longitudinal wave, strain wave, for better protection. So, PM Cunniff actually deducted one, that dimensionless property, fiber property U, particularly for that impact ballistic protective purpose. Okay. That is U. U can be given as this relationship where the sigma is the tensile strength of the fiber. This is the tensile strength of the fiber, epsilon is tensile strain of the fiber, Young's modulus E, and rho is the density. Now, here you can see this actually denotes the energy absorbed, energy required for breaking. It is not exactly energy, but it this strain and tensile strength and strain, if we have these two, that means if we have higher tensile strength, then we will have higher U value. Higher tensile strain will have higher value. Higher Young's modulus we will have higher U value, and lower density we will have higher U value. So, effectively you will see these two are related with the. So, U actually is proportional to C, U is a so U indirectly, you can say directly U actually represents the longitudinal strain value. If we have say this break tensile strength, tensile strain and rho constant. So, these are basically related, and if the rho is constant also, that means Young's modulus is the characteristics which actually controls the C value. So, based on that, for different fibers we can derive the U value. So, and U value shows directly the impact characteristics, that is the ballistic impact behavior. So, here E is the specific toughness of the material. Now, we can see here these are the different fibers where we have the density value, we have the elastic modulus, we have tensile strength and tensile strain we can get. So, from this all this data we can get the U value, which was actually discussed in earlier. U can be calculated. So, let us see the U value, fiber properties are there, and these are the U values. That means, higher U value means higher ballistic characteristics. So, ballistic figure of merit, the U is known as the ballistic figure of merit, U power 1/3, and here higher U value. So, like cotton has U value of say 348, that may not be useful for ballistic protection. So, here at this range we use these fibers, we use the fiber like Kevlar, even Spectra, typically around say 700, 600 to 800 range. That is the typical fiber used for the ballistic protection. but in futuristic, if we use say spider silk, if you see it is 930 around, or maybe carbon nanotube. Okay. So, carbon nanotube, if you see, we can have say 4000, more than 4000 U value. So, these are all the future armor. For future armor, we have to go for this. Next parameter is the projectile geometry. So, projectile geometry, there may be different types of projectile geometry. So, available projectile shapes are hemispherical, conical, fragmented and flat. And also the pointed bullet is there, which causes the severe action. So, there may be a pointed bullet, may be hemispherical, conical, fragmented and flat. So, let us see these shapes here. These are the different shapes. This is the hemispherical, at the tip the shape will be hemispherical. Typically for standard bullet, it is the radius here of the sphere, hemisphere is 6.35 millimeter, and the length here is 9.9 millimeter and diameter is 12.7 millimeter and overall length is 16.3 millimeter. That is the typical dimension. For conical, here this angle is 151, that is the angle. You can see this is the angle. And now conical angle, this will be the angle, conical angle, it is 151 degree, and here 16.5 is overall length and the 12.7 is the diameter. Now, if you see the fragmented, there will be a flat portion. The flat portion, this dimension is at the top, it is 8.9 millimeter and this angle is 111 degree and effective length is 15.2 millimeter and the diameter of the that bullet is, that projectile is 12.7 millimeter, and for flat it is that basically the diameter is typically it is cylindrical shape. So, with a 12.7 millimeter diameter and the length is 14.2 millimeter. So, that these are the dimension. On that different studies have been carried out. Next is the impact angle, which is very important. As per the standard, the impact angle should be this 90 degree. Okay, that this is the impact angle. If we see it is 90 degree, or sometime it is called 0 degree angle, but this is 90 degree effectively. If we have the angle of impact at lower angle, so if we reduce the angle, then what will happen? There will not be that penetration will not be there. The projectile will slide, and what will happen? There will be more frictional effect. So, at low angle, that projectile will simply slide past and there will not be any impact, no penetration will not be there. Okay. So, there only a frictional effect will be there. Now, impact angle between 30 to 45 degree, lesser time for energy dissipation, and again the frictional effect will be there. Okay. But when the angle is 90 degree, that is 90, only perpendicular area is contacted, no sliding will be there. So, that at different angle, if the projectile hits at certain angle, so there will be frictional loss will be there. So, penetration will be less, but when there is a 90 degree impact, that means the only peripheral areas will be in contact. Suppose this is our material to be tested and here the bullet is hitting at 90 degree. So, only the peripheral area will be under contact, there will not be no sliding effect. So, due to this friction, whatever energy has to be absorbed, that will be only due to this friction of this the peripheral area. But if there is a sliding, then the energy will be absorbed, energy of the bullet or projectile will be absorbed by the friction also, sliding friction. This we can see here in this picture. If the profile is this, angle of impact is, this is suppose this is the angle of impact and here is the nose and this is the material, and this angle of impact will have basically a sliding effect, because the for penetration we need a component, downward component, it will have two components. One component will try to, this velocity will have two components or this force will have two components. One will be, this force will try to slide this, and another force which is downward will be actually used for the penetration. So, if the angle is low, okay, then sliding force will be more, and that will actually have the frictional loss will be there. And impact velocity has got some effect, and it actually determines the contact duration. If the higher velocity is there, then the contact duration will be low. So, with the increase in this impact velocity, so energy absorbed, as the velocity is low, at lower velocity there will be definitely lower energy absorption, but as the velocity increases, so the kinetic energy will be more and more due to the velocity, and energy absorption by the material will increase. So, this is straightforward, but when the velocity is beyond certain critical value, like at level 3, that contact duration will reduce, and due to the high velocity, that frictional resistance will be less and energy absorption will be very low, because it will actually at higher velocity that will penetrate without any much frictional resistance. So, that is why the energy absorption will be lower, very low. So, for that, this is a particular for a particular type of fabric. So, we have to actually increase the energy absorption, we have to increase the contact duration. So, for high velocity, if we want to increase the contact duration, so we have to use a thicker multi-layer fabric, multi-layer cloth. So, in that case the duration will be contact duration is increased and energy absorption will also increase. So, for the at the level 3, so if we have to, then we have to use the multi-layer fabric, number of layer if we increase, then this energy absorption will be high. Now, these are the different shapes as we have already discussed. Now, let us see the impact of this different shapes on the perforation characteristics. Now, A, B, C, D, A here you can see this is A hemispherical. So, A here it is showing the fragmented that simulating that it is a back face damage for 6.5 millimeter thick panel. So, we have two different panels we have produced, and this with the you can see this is the fragmented with this type of shape at the tip, and we are looking from the back face. So, at the back face that this type of damages will be there, okay, with a 6.5 millimeter thick, and B is the hemispherical. The type of damages are different, and C is the conical damage, and D is the flat projectile. Here this is a flat you will see that this tearing will be much higher here. So, this all this values have been measured. So, depending on the shape of the projectile, the type of damages, shape of damages are different. Now see it is a thinner 3.2 millimeter thick panel. Here the shapes are different. You can see the fragment simulating, flat B, C is the hemispherical and D is the conical projectile. Here the conical. So, now if we see the energy absorbed at the ballistic limit velocity for each specimen, what are the different types of energy absorbed? Now, try to see like for conical with that 6.5 millimeter thick panel absorbs much more energy than the 3.2 millimeter panel. So, because of the thickness it actually takes load and there will be frictional loss and the higher dissipation of the energy will be there. So, energy loss will be energy absorbed at thicker panel will be higher than the thinner panel. Now, for 6.5 millimeter thickness thicker panel, the conical, the projectile with conical tip results highest energy absorption, followed by the flat one, then hemispherical, and then the fragmented. Fragmented absorbs the least energy. Similar trend is also observed for 3.2 millimeter thickness. So, for fragmented that projectile, so the energy absorption will be least. Now, that in earlier picture we have seen that there are cracks, it is a transverse crack and this is the longitudinal crack, okay. Or you can say this is a different types of cracks are there. So, this crack growth, this is the transverse crack and longitudinal cracks. So, this crack growth, they depend on the this shape of the projectile. Now, here we can see this is the for 6.5 millimeter, this is 3.2 millimeter, and this one, this plot is for transverse growth, that is a longitude, that is this is the longitude, horizontal transverse growth, and where you will see the conical, although it is having higher, absorbing higher energy, mainly due to the crack flow, it growth, crack growth is maximum, and for fragmented crack growth is minimum. So, higher crack growth means higher energy absorption. The similar trend is also there for 3.2 millimeter, although some deviation here for flat one, particularly for 3.2 millimeter, but trend is almost similar. But if you see the longitudinal crack, the trend is not that clear trend. This may be due to the different shapes. So, we have discussed the effect of different shapes of the projectile, and we will stop at this point. In the next session, we will discuss methods of performance evaluation and different other aspects of the ballistic protective textiles. Till then, thank you.